I'm back in college. So this for an ideal gas, we've looked at what a gas is, and those are the assumptions, those 5 assumptions. Many molecules in rapid random motion, that the volume of those molecules is negligible compared to the size of the container, that the forces those molecules experience is 0 except during collisions, that those collisions are perfectly elastic, and that the time taken for those collisions is negligible compared to the time between those collisions. Those 5 assumptions are essential, and you'll see as we move through this book they start to underpin more and more of the larger scale mechanics of a gas. In the second video we looked at what a gas does. We learned about these laws. We have Boyle's law for pressure, Charles's law for temperature, and we learned that this temperature, in order for it to work properly, that there is actually an absolute minimum temperature we can possess when we remove all of the kinetic energy in a substance. That is minus 273 degrees Celsius, or as we'll just call it now, 0. Why not? 0 Kelvin, that is. And we linked together all these properties. I just wanted to show you the units that we have to use for all of these things as well. Pressure is obviously measured in pascals or newtons per metre squared, same unit, remember. Temperature, that has to now be the absolute temperature in Kelvin. Remember, this will not work if you use degrees Celsius, because you'll end up with putting 0 degrees in, the volume will be 0, and that can't be the case, otherwise we'd all asphyxiate and die when it froze outside, and that wouldn't be very nice. T now has to be the absolute temperature, and you will hear me refer to this absolute temperature, an absolute temperature scale. That means in Kelvin, starting at 0 and only ever getting bigger. That means on the scale where we cannot have negative temperatures. Remember, the conversion between degrees Celsius and Kelvin is just to add 273.15. The volume of our gas has to be measured in meters cubed. Think for a second about a potential pitfall here. If you're working with meters cubed, what if you're given a volume in centimeters cubed? You have to remember to divide it by 100 cubed. Remember your volume conversions. Whatever the conversion would be for meters regularly, you have to cube that conversion. It's a dead easy thing that you should have been used to. Just in case you're not, thought I'd remind you. These gas laws are really nice. We have Boyle's law, pressure is inversely proportional to volume. We've got Charles's law, temperature is proportional to volume directly. We could have any number of proportionalities. And I know that you're probably saying, if you're switched onto this, you're probably saying in your head as well, Rob, you've never actually stated Boyle's law as the definition in the book says. And that's a really good point, because if I was to state Boyle's law in that way, I'd have to admit that there is a limitation to this proportionality. Both Boyle's law and Charles's law, the pressure volume and the temperature volume laws, only work in one specific circumstance. They only work for a fixed mass of gas, keeping everything else constant. So let's look at Boyle's law. Boyle's law states that pressure and volume are inversely proportional for a fixed mass of gas at constant temperature. Great. But how often does that situation apply when we have a fixed mass of gas at a constant temperature? Charles's law, the temperature one, this law only works for a fixed mass of gas at a constant pressure. So these individual proportionalities, whilst they are useful from time to time, they never tell the full story. In order to put all of these measurable properties together, we have to incorporate the amount of gas. That's what we're going to look at today. Amount of something actually has an SI base unit. The SI base unit for amount of substance is the mole. Before I can combine all of these proportionalities and correctly define an ideal gas, I think it's worth just talking about moles in detail. Moles is one of those topics where I would say put your hands up if you like moles, and maybe like 2 people would put their hands up, and put your hands up if you don't, and everyone else would be like, oh yeah, I don't like moles. So what I'm going to do now, I'm going to invite you to cast aside any negative memories that you have of moles. Please put them away, forget that it ever happened, let's start afresh. Embrace this opportunity to understand moles a little bit better. Moles in physics in ideal gas are very simple, and I want to keep it that way. 1 mole is quite simply this. It's a specific number of things. 1 mole is 6.02 times 10 to the 23 objects. If you have a mole of something, you have 6.02 times 10 to the 23 of those things. 1 mole is just a number. It's got nothing to do with chemicals. It's got nothing to do with chemistry even. This number here, 6.02 times 10 to the 23, is called Avogadro's number. That's after the guy that kind of came up with it. So 1 mole just contains 6.02 times 10 to the 23 things, and that number is called Avogadro's number. You'll see it in some equations later on. Save us right now every time. There's nothing more to it. A mole is a lot of things, exactly 6.02 times 10 to the 23 to be precise. That is a very big number. Just to invite you to experiment with this number, to play with the idea of a mole. You could work these things out, and I would normally in lessons invite people to do these, so I'm going to put it up on the screen, you have a go at them, check that you're comfortable with moles, and then I'll put the answers up and you can move on. So how many particles are there in 0.67 of a mole? How many particles are there in 4.93 moles? Alright, those are easy. If there's approximately 7 billion people living on Earth, how many moles of people is that? You might notice that even 7 billion people, so that's 7 times 10 to the 9, that leads to a very small number of moles, because this number, 10 to the 23, is vast. And that should tell you kind of just how small atoms are. There are that many of them in just 1 mole. You probably did these calculations without thinking about them, or at least I hope that you did. Because these are dead easy maths calculations, these are just quick conversions. Okay, there's no advanced maths done at all here, other than using the times 10 to the 23 button on your calculator. It's dead simple. And just to clarify the calculation that you would have been doing there, you've taken the number of moles and times it by Na for Avogadro's number, you've converted it into the number of particles. And for the human moles one, you've just rearranged it and you've said, oh, okay, the number of moles is the number of particles divided by Avogadro's number. It's a dead simple calculation, and this is what we will be working with largely in the next part of the book. But Rob, different objects have different masses, not every gas is the same. How do we incorporate that? Well, there's one extra tiny thing to do with moles. You might notice that in Boyle's law and Charles' law, they actually talk about a fixed mass of gas. The fact that the mass of gas is different is incorporated using this feature. We talk about molar mass, known as MR. It's quite simple. The molar mass tells us the mass of 1 mole. The molar mass is simply the answer to the question, how much does 1 mole of this gas weigh? For example, carbon by definition has a molar mass of 12 grams per mole. How many grams of carbon are in 1 mole of carbon? It's not a trick question. How many moles of carbon are in 60 grams of carbon? You getting the picture? So, how many atoms are there in 48 grams of carbon? I'll put the 2 ideas together now. So this idea of molar mass, again, it's a straightforward idea which perhaps was overcomplicated or not explained to you in a clear way at GCSE. We have 1 mole, which is simply 6 times O2 times 10 to the 23 things. And we have molar mass, which is how much does that actually weigh? What is the mass of 1 mole of substance? You will always be given molar masses in the question. Quite often, if you do chemistry, you'll notice the molar mass is the same as the atomic mass. Physicists, you'll just be given this number and you need to recognise it. An important thing to bear in mind is this grams. Just bear that in mind. If it's given to you in kilograms per mole, that's fine, do nothing. But just read. Number 1 cause of lost marks in physics is people not reading the question. The equation here that I find fairly easy to remember, moles equals mass over mR. The number of moles is the mass that you've got divided by the mass of 1 mole. Makes sense when you read equations back to yourself like this, doesn't it? And just explain to yourself what they mean. So that's my brief summary of moles. Let's now look at how this is incorporated into putting our gas laws together. You'll be glad to know there's no derivation of the ideal gas equation. All you need to know is the equation that drops out. And you'll be glad to see that this incorporates all of those proportionalities into one dead simple equation. Learn it, ladies and gents. This is the ideal gas equation. Pressure times volume equals number of moles times a constant times the temperature in Kelvin. PV equals nRT. This number R is just called a gas constant. It's in the front of your equation sheet, it's also on your calculator. R is just 8.314 joules per mole per Kelvin. This is probably one of my favourite equations in the whole of physics. I've used this equation all the time, and so will you. PV equals nRT, the pressure in the gas times the volume is equal to the number of moles times the gas constant times the absolute temperature in Kelvin. That's what you need to be careful with here. As I said before, pressure needs to be in pascals or newtons per metre squared, volume needs to be in metres cubed, N needs to be in moles, R, you can work out what the units of R have to be, and T has to be the absolute temperature in Kelvin. Reason being, it's the same as before. If you use degrees C, then when this was 0, this whole equation would go to 0, and that doesn't make sense because at 0 degrees Celsius we can still walk outside and we're just fine. Here we need to use the absolute temperature in Kelvin. Gas constant 8.314, just something to remember. But Rob, there's another version. Yeah, there is another version. This is like the evil twin of the ideal gas equation. It tells you the exact same thing, but I personally try to never use it. I like to just remember one thing, keep things dead easy, but do be aware that this works. You know, if for some reason I want to work out the individual number of atoms in that sample, if I just want to blow people away with big numbers perhaps, or maybe just avoid moles, which you shouldn't, moles are nice, then PV, pressure volume, equals capital N times kBT. The two things that have changed in this equation become capital N, that is the number of individual atoms. So that number is going to be absolutely enormous. Capital N is a capital because it's going to be big. Capital letters mean big things. And in this case, KB, it's called the Boltzmann Constant. Again, it's in the front of your formula book, it's on your calculator. It's actually the gas constant divided by Avogadro's number, because all we've done is convert n moles into n things. This is the exact same equation, but tells you for individual particles. I personally have no idea why it would ever be useful to know the exact number of particles in your gas. It is an enormous number, and so by extension it is meaningless. However, later on when we look at kinetic energy per mole, I will admit this is a useful equation. Right now though, what you need to do is to fill in this section on the ideal gas equation and go and practice. Part 1 really goes to town on PV equals nRT. Like I said, this equation will never go away. you need to become best friends with the idea of moles and best friends with this equation. So I'm going to say no more except get practicing ideal gas and moles.